In this video, we review the basic integration formulas and one very important basic integration technique called substitution. In Calculus 1, we learned some basic integration formulas. Here is the list. Formulas number 1 to 9. Those are integration formulas we learned before. And in this course, we added 3 more formulas involving inverse trig. Now, rarely could we directly apply some of these formulas to evaluate integrals. Most of the time, we need to do some substitution. So in this section, when you see how we generally try to come up with appropriate substitution to evaluate different integrals. Some of these integrals we'll try to come up with a substitution so we can make use of the first 9 formulas. Others we'll see things to do in order to use these new integration formulas. Substitution is so important that we pretty much do it everywhere. Anytime we integrate, there's always some kind of substitution necessary. This is why we want to review this material before we get to other integration techniques in this course. Now, before I get to the problems examples in this section involving substitution, I want to talk about one thing I came up with called supporting factor in substitution. It's important, it's useful to know what this is about. So it's going to help us, better decide, more quickly decide whether we can do any substitution. Alright, let's see examples so you get the idea. Say I have a x squared sine 4 minus x to the third power dx. Pretty common integrand. This problem, well, you'll see we have to do some substitution. Now, the way I approach integrand is I try to see if it involves 2 parts. Okay. Well, this is a product of 2 factors, so there are 2 parts involved. Sometimes in a fraction, division, 2 parts, top, bottom, product, 2 factors, 2 parts. So I usually try to see what substitution I can use to simplify the more complicated part. Well, the way it usually works out is this: if we can simplify the more complicated part, or less complicated part can be hopefully taken care of at the same time naturally. So let's focus on this more complicated part. Now, whatever substitution we want to consider, the goal is to hopefully reduce this to some simple structures here. So we can apply formula directly, like simple power can be 1 over the variable, or e to this plane variable, or cosine variable alone by itself, just u, not 2 times u, not u squared, not u divided by 5, or similarly sine u, and so on. So with this simple criteria in mind, we can see in order to simplify this more complicated part, it's natural to try 4 minus x to the third power. With this more complicated part can be reduced to simply sine u, which we can integrate directly by applying the formula. Alright, so well, turns out this is the substitution when you need. So let's continue. This is our substitution. So this part becomes sine u. What about the dx? What about the x squared? Well, let's work on the side, see how we can get rid of the dx. What we can plug in for dx? So this is the routines. U equal to 4 minus x to the third power. You differentiate. Negative 3x squared multiplied by dx. That's the differential of the right hand side. So from here, you see the dx that we want to get rid of. You also see x squared that needs to be replaced too. So at the same time, we can replace x squared and dx by that. You just solve for x squared dx, the combination. So the x squared dx together is replaced by basically we have a rather simple integral. And use the formula to finish up. Integral of sine is negative cosine. And simplify positive cosine, bring back the expression for u. Now this is how we do substitution, how we evaluate the integral with the sum substitution. But what I want to talk about really is the supporting factor. What's the supporting factor? X squared is supporting factor. This guy is what I call supporting factor. You can see when we introduce u equal to 4 minus x to the third power and do the differential both sides, we got the perfect x squared with a dx, and that's exactly the thing we wanted to replace besides the dx. So this x squared is just perfect. It's just the correct, exact factor we would want to see. If it's any different, if it's not x squared, say x to the third power, then we would be in trouble, because with this differential identity, we can take care of x squared at the same time with dx. With x to the third power, then we would have a leftover, because the x to the third power, you can think it's a it's square times x. Sure, we can use a square to go with the dx. The square can go with the dx at the same time, replaced by whatever. There's a leftover x. So that something that would be something that's going to still stay, which would create problem, which would make the substitution not work. So x squared is what I called supporting factor, nothing else. X third power, like I explained, it's not going to work. If it's a first power, you may think it's a simpler, right? Well, it's not going to work, because again, if it's only x to the first power, then from the differential identity, we need x squared. Alright, so x squared again is what I call supporting factor. Before we even started the whole thing, to try out, check it out, work it out, it's helpful to quickly see whether there's any supporting factor in the integral. And we don't have to write it down and do the differential to find it out. Just a simple differentiation. Say, start from beginning again. So, given this integral, naturally, we want to consider u equal to that. Then just, without writing down anything, we just do differentiation quickly in our head. So let's differentiate this. What would we see? Derivative 4 is 0. Derivative of x to the third power is negative 3x squared. Negative 3 will not matter. It's going to just become some coefficient in the front, as you saw in this example there. So we never worry about the constant factor. So basically, you differentiate, you would see like x squared. You see x squared there. That means you got the supporting factor. Alright, let's see another integrand so you understand this supporting factor idea better. Negative 3x cube the root of 4x squared plus 9 dx. So this is a very typical structure, two parts. This is more complicated, so we want to simplify this, hopefully by using some substitution. Now, in order for any substitution to work, say if we can reduce this expression to cubic root of u, that will be just a simple power of u that we can integrate, right? So naturally, we want to consider this to be u. Well, let's differentiate. If we differentiate this u thing, we get a times x. A is a constant, we don't care. X is a factor that we would really want to have to make the substitution work. And we have x right there. So we have the supporting factor. If we work out, then this can be turned to very easy, just some constant. That's a simple power that we integrate, right? So this is what I want to talk about. Supporting factor. For u equal to 4x squared plus 9 to work, we better have first power of x. So this supporting factor basically is sort of like a derivative of the substitution you have in mind. It's really that simple. Okay, and so hopefully you get some idea about this supporting factor, because I'm going to use this terminology, this phrase a lot when I try to decide whether substitution would work or not work. If I think it's going to work, if I think there's a perfect supporting factor in place, well, it would work. I would continue. If there's no supporting factor, I'll forget about it. I'll try something else. Alright, let's see example. So first example is x squared times square root of whatever here. So two parts, x squared and the radical, two parts. Radical is obviously more complicated, right? So let's use this supporting factor concept to test out before we actually write down anything. So naturally, I'd like to simplify the more complicated part with, say, u equal to 2x third power minus 4. Let's differentiate this guy. It'd be 6 times x squared. Don't I have x squared here? Exactly, right? So I have the perfect supporting factor. So I know it should work out. So let's go ahead and see if that's the case. This is our substitution. So you find the du 6 x squared dx. Derivative of that is 0. Okay, so it's the 6x squared. Now the radical becomes square root of u. From the differential identity here, x squared and the dx together is 1 over 6 du. Well, this part becomes square u. We're left with the dx and x squared. See perfectly, x squared dx together 1 over 6 du. Just perfect. Well, because we have the perfect supporting factor that supports our substitution, basically. That's why I call it supporting factor. 1 over 6, and this is just a power. Apply simple integration formula power rule. U n plus 1 over n plus 1. This is n. Alright, and further simplify, this is 3 over 2 or 2 over 3. To flip it, the u 2x to third power minus 4. Pretty much done. I mean, you can simplify a little bit, cross out 2 and so on. That's okay. So you can see the analysis involving supporting factor I was doing before I start to actually write down anything. Okay, next let's see this integral. Again, I want to talk about supporting factor. So that's the thing, that's going to really determine very easily whether any substitution would make sense or would work. Alright, first of all, 2 parts. This is e2 something times square of cosecant. So 2 parts. Which one is more complicated? This is more complicated. It's exponential with the trig in exponent. More complicated. And naturally, I would like to consider this to be u. So that would be my substitution, right? And let's differentiate. See if I got perfect supporting factor. What's the derivative of cotangent? Well, it's a negative cosecant square. Negative is just a -1. It's like a constant we don't really worry about. So what's important is derivative is will give us cosecant square, which is what we exactly have. So I say we have perfect supporting factor here, which means this substitution will work out if we do it right. Alright, let's get started. So this is my substitution, so that's e to u, and the du equal to, differentiate, like I said, the derivative of cotangent is negative cosecant square. This negative, so there's just cosecant square. Negative and negative cancel each other. Well, actually it's perfect. The combination we see is what's left to be replaced in the integral. So the old integral becomes a very simple integral. The applied formula is e to u plus c. Done. right? So you can see from these two examples, it's helpful to check whether there is a appropriate supporting factor in place for whatever substitution you have in mind. Okay, let's continue to see substitution and the analysis of supporting factor for whatever substitution you have in mind. This is another typical substitution problem. Let's see, two parts, the bottom is more complicated. So again, we would try u equal to 4 minus x to the fourth power. Differentiate that thing, you would have, well, derivative of 4 is 0. Derivative power is 4 times x to the third power. We just happen to have x to the third power, and that's what I call supporting factor. So I know before I even start out, u equal to this thing as my substitution will work out. This is to give you another example. Also, it's a problem that I want to show you. It's a comparison to the next one. Okay, won't hurt us to see another example of sort of a direct substitution. So let's write it down. U equal to 4 minus fourth power my substitution. The integral becomes square root of u on the bottom. Now the top, well, du equal to negative 4x to the third power dx. X to the third power times dx. It's negative 1/4 du. And it's x to the third power dx together, right? Replaced by negative 1/4 du. Divide them. So move out the 5 for the radical. It's half power on the bottom. Move to the top, becomes negative. So this is just another, again, simple power to integrate with the formula 1 over n plus 1 u raised to n plus 1 plus c, and then simplify the coefficient. So half, flip it, becomes 2 on the top, so it's 5 over 2, and the u is 4 minus x to the fourth power, positive half power plus c, and done. So this is just another example how we do substitution, how we analyze before we actually do anything, whether there's a supporting factor. Okay, like I said, another reason I was doing these examples in comparison to this guy, but let's see, they look very much similar. Of course, I purposely constructed the functions to show you some similarities, differences. Well, given this integral, naturally we want to try see if there's any substitution that will work out, right? So two parts. This is more complicated as usual. So I'm going to try u equal to 4 minus x to the third power, hoping I get square u on the bottom, integrate, that kind of thing, right? Well, it turns out u equal to 4 minus x to the fourth power, right? If that's my substitution, I would want to have x to the third power as what I call supporting factor, right? What do I have in this problem? I only have x to the first power. I don't have x to the third power. And well, this one, of course, like I said, I purposely put it here so you can compare those two. This one we did. We had the perfect supporting factor. Not here. Now this says u equal to 4 minus x to the 4th power will not work. Then what do we do? Well, this time we try something else. Substitution, direct substitution is not going to work out. Because of the special structure here, fraction, it's one thing. It's a radical, it's a number minus thing. We can try to see whether any of those new integrals would work. See, they're all fractions, right? In particular, those two are fractions involving radical on the bottom. Okay, so if you see fraction, you see radical or sum of two terms on the bottom. You probably want to try seeing if any of those would work out. For any of these to work out, you have to have a square. U square here, U square, U square here. So let's try 4 minus, let's come up with a square. So our hope now is we can introduce a substitution, and this inverse trig related integrals can be applied. Now first of all, we need to have a square. So look at the radical. Here we rewrote x to the 4th power as a square raised to the square. So my substitution this time will be this guy equal to u. So this is what I have in mind. U equal to x squared. Again, do I have the perfect supporting factor for this substitution to work out? Differentiate x squared. It will be 2 times x. You see the x there? If we try u equal to x squared as our substitution, I have the supporting factor there. So this just says it should work out. Let's put it in writing. So u equal to x squared, du equal to 2x dx. The integral becomes on the bottom 4 minus u squared that we want. The 5 copy down, and then x and the dx together. This is the supporting factor we actually have. So half du with the constant all pulled to the front. So we see an exact integral like this. Number minus square. Number minus square with the a equal to 4. I mean a equal to 2. So we can apply formula. Number 10. Inverse sine u over 2. A is 2. U is x squared plus c. Okay, so with these two examples side by side on the same page, you can see how we again try to use this idea of a supporting factor to see whether it will work directly or it will not. Okay, so directly for this guy we want to try substitute u equal to 4 minus x to the 4th power. You differentiate, you get the 4 times x to the 3rd power. Yes, we have a supporting factor. For this problem, if you try the same direct substitution to try to turn this into simply square u, it will not work out because x is not supporting factor. Fortunately, for fraction with the radical, sometimes we can try this or this, or even fraction with the sum on the bottom, we can try this. So in this integral, we can rewrite the fourth part as a square and try a new substitution with a different formula in mind. Now this substitution u equal to x squared, of course, I showed you, I checked out the supporting factor too to find out, yeah, I get x, the perfect supporting factor to make it work, and then I start to work it out. Alright, so supporting factor, very important concept. Let's see one more example, and then we'll try supporting factor, so on. Okay, so this is x to the third power times square root of whatever, radical. Okay, two parts. Second part is more complicated. So naturally, we'd like to simplify this radical portion. The substitution we would use would be u equal to 2 minus x squared. Right? This way, this radical expression will become simply square u, simple power, maybe we integrate. Alright. Well, the problem is the natural substitution will be u equal to 2 minus x squared. It doesn't seem to be correct though. Well, why? If our substitution, we're using the supporting factor to check this out. If the substitution is u equal to 2 minus x squared, we differentiate, it'll be negative 2 times x first power. What we have is x to the third power. That's not perfect supporting factor. If it was just x, that'd be perfect. And we have a perfect supporting factor, and the u equal to 2 minus x squared, we know it would work out for sure. Third power, well, it seems like the substitution would not work out. Well, here's an exception. When we first check, using this supporting factor, then looks like it will not work out. Well, the thing is, turns out it will somehow, but not in the usual way I explained to you. The substitution would still work. Well, how do we know? We just have to try. Now, why would we try this? There's nothing else we can try. Okay, so two parts. We got to simplify the more complicated part, even though initial check shows that we didn't really have the supporting factor. Truth is, there's no other way we can do it. It's not even like a fraction. We may try to say, hey, maybe inverse trig related integrals would work out. There's nothing else would work out. So let's give it a try. With this substitution, du equal to negative 2x dx, right? So let's see what it means. Square root of 2 minus x squared becomes square u. There's dx. There's x to the third power we want to get rid of. Unfortunately, from the differential identity, we can only use one copy of x. Go with the dx. So this just shows first power of x with the dx can be replaced back, right? This is why the normal supporting factor idea, shows it would not work out. It would not cleanly get rid of the leftover. That's really what it is. well, we do what we can. So from this identity we say let's get a copy of x to go with the dx. 3, right? So let's get a copy, split it as this. So this one copy of x will go with the dx, x times dx, replaced by half du. So normally it would not work because there's leftover, right? So there's still x squared left. Fortunately, because of the special substitution we use, from the substitution itself, we find out if we move x squared to this side, u to this side. So x squared actually equal to 2 minus u. We can still get rid of the x squared, the leftover. Not cleanly, not like usually would go away. At the same time, dx get replaced by something like this. Okay, so this problem, there's leftover. Well, we can replace x squared at least by 2 minus u. So at least we still have like a new variable containing entirely new variable u. Not so complicated. This is not too bad. Alright, so the question is, can we integrate this? Yes. Negative half, pour out. This, if you write as a power, and then you multiply through. Now, it's very important that you have to multiply through before applying any formula. Cannot integrate the power here, and the 2 and the u in this product. There's no such product rule in integration. Okay, so you multiply through. Let's see, 2 times u reached the half power times u, this is the first power, so it's 3 over 2. So it turns out we can still integrate fairly easily. So power 1 over half plus 1 u half plus 1 minus 1 over power plus 1 u power plus 1 plus c. This is 3 over 2, so 2 over 3, so it's 4 over 3. 2 minus x squared, 3 over 2. And this 5 over 2 becomes 2 over 5. 2 minus x squared, 5 over 2. Just algebra simplification. Okay, so this is an exception. The usual supporting factor check showed the substitution, the natural substitution should not work out. That's because it's in some way still kind of a nice factor, although not what we consider as a perfect supporting factor. We were able to still get rid of everything, get rid of all x basically. Okay, x squared left over replaced by 2 minus u, and then we can still integrate. Alright, so to keep in mind, most of the time, you do integration and come up with some substitution in mind. Check, see if you have a perfect supporting factor. If not, a few things you can try. If it's a fraction with a radical, maybe you can turn your expression to 1, so you can use the inverse trig related integrals. like this one. You check the supporting factor. Perfect supporting factor would be third power, right? Well, we don't have that. So this problem turns out, because it's a special function here, it's a fraction with a radical, then we try to say, hey, can we turn this into 4 minus u squared? Inverse sign in mind, the formula. So this works out. Or occasionally, like this, you do the supporting factor check. U equal to that. We don't really have that. Turns out it would still work out. Just exception. Alright?